Okay, in this video, we're going to study um, a topology on a subset Y of a topological space X using a topology of X, and that topology on Y is called subspace topology. Now, let me give you the formal definition of subspace topology, and then I will give you a few examples. Okay, so here is the formal definition of subspace topology. Definition. So let's say X is a topological space. X is a topological space. X is a topological space with with the topology tau, and let's say Y is a subset of X. We have a topological space X with the topology tau, and Y is a subset of the topological space X. Uh, then the collection, then the collection, then the collection uh, tau Y U intersection Y such that U is in tau. So basically this collection, so in this collection or the element of this collection, to get the element of this collection, what you need to do is we need to take the intersection of this subset Y with each subset of X. That means you take the intersection of Y, not each subset, we take the intersection of Y with each open set in X. So basically, to get the element of this collection, we need to take the intersection of Y with each open subset of X. That means with each element of the topology tau on X. So if you take the intersection of Y with an element of this topology tau, then that intersection is gonna be an element of this collection. So basically this collection is the intersection of Y with each element of tau, and this collection is a topology on Y, and this topology is called the subspace topology. It's called the subspace. It's called the subspace topology. It's a subspace topology. So as I said before, to get the element in subspace topology, what we need to do is we need to take the intersection of Y with each open set in X. That means you take the intersection of Y with each element of the topology tau. So that will give an element of this subspace topology. And if you take the intersection of Y with all the element of this topology tau, then that collection is that collection give us subspace topology. And with this topology tau Y, with this topology tau Y, this subset Y is called a subspace of X. Now this is the formal definition of topological space. Now let me give you example, or before we give an example, let's prove that this collection. So here we have simply said that this collection tau Y forms a topology on Y. Now let's prove that this collection forms a topology on Y. Okay, so we're going to show that this collection is a topology using the definition of the topology. So if you go back to the definition of topology, a collection of the subset in a given set is called the topology if it satisfies three properties, and one of them is the empty set and the whole set. It has to be in that collection. So since we are saying that this tau y is a topology on Y, so the empty set and the whole set Y, they have to be element of tau y. In fact, they are the element of tau y because we can write down phi, or that empty set, in this form, and also we can write down y in this form. So how? This is how we can write down this empty set in that form. We can write down empty set is, if we take the intersection of empty set with y, then we're gonna get the empty set. And obviously this intersection is in this collection. So in order to be this intersection in this collection, you need this empty set. Like here u, it has to be in the topology tau, and the empty set, it has to be in topology tau, and obviously empty set is in the topology tau. And also the y, it can be written as in this form. So if you take the intersection of x with y, x intersection y, since y is the subset of x, so x intersection y is gonna be y. So we have rewritten y in this form, and then the first set x, like here u, it has to be in the topology tau, and x, it has to be topology in tau. Since tau is the topology on the set x, so obviously empty set and x, they are in topology tau. So where empty set and x, they are in tau. So that means this collection satisfies the first property of topology. And the second one, if we take the arbitrary union of the elements of this collection, that union, it should be in this collection. Okay, to prove that one, let's suppose u alpha intersection y, this is the family of elements. This is u alpha intersection y, that's the family of elements in this collection. So where, or instead of where, let me just write down for an index alpha in the index set, in the index set, let's call that index set is j. So here we have taken the family of element from this collection. Now we need to show that the union of this collection, just the union, this is union of this collection, it has to be also in tau y. And now you can see in this union, so what we are doing is we are taking the intersection of y with u alphas. So those u alpha, since u alpha intersection y is an element of this tau y, so the first guy u alpha, it has to be in the topology tau. So this u alpha, which are the arbitrary collection of the or you can say the family of the elements in tau. So we are taking the intersection of y with each of u alpha, and then taking the union, so which is going to be same as you first take the union of those u alphas and take the intersection with y. So it's basically, first you take the union of u alphas and then take the intersection. So taking the intersection of y with each u alpha and then union, that's gonna be same as first you take the union of u alpha and then you take the intersection. Now where, So where, since like I said earlier, these u alphas, they are the arbitrary element in tau, because this u alpha intersection y is in tau y. In order to be this guy in tau y, u alpha, it has to be in tau. So this u alpha, there, that's the arbitrary collection of arbitrary collection of the elements in tau. And if we take their union, that's also, it has to be in tau, because tau is the topology on X. So where union of u alpha is in tau. So now you can see here, so the right side is the intersection of an element in tau with y. So if you take the intersection of an element in tau with y, that's gonna be one of the element in tau y. So that means this guy, so this implies that union of u alpha intersection y is also in tau y. So so this shows that arbitrary union of the elements in tau y is gonna be in tau y. That's the second condition. Now we need to prove the third condition for the topology. Third condition for the topology is, if you take the finite intersection of the element in tau y, that intersection should be in tau y. Now let's suppose let's assume that u1 intersection y, u2 intersection y, up to un intersection y. So we are taking the finite number of elements in tau y. So that means where u1, u2 up to un, these are the elements. These are the elements in tau. So suppose these are the finite number of elements in tau. Now what we need to do is, we need to show that their intersection. So if you take the intersection of all these finite number of element in tau, their intersection also, it has to be in tau. So basically here I runs from 1 to n. So if you take if you plug in 1 for n, or 1 for I, that's gonna be u1 intersection y, that's first set. And then u intersection, you plug in 2 for I, that's the u2y, u2 intersection y, and then you keep going. So this is the this gives us the intersection of those elements in tau y. Now we need to show that this intersection also in tau y. Now here what we are doing is, we are taking the intersection of y with each ui, with each ui, and then we are taking the intersection. This is going to be same as, you first take the intersection of ui's. So you take the intersection of those first un, and then take the intersection with y. So these two sets, they are going to be same or equal sets. So where now we know that this u1, u2 up to un, they are in tau, because these intersection, they are in tau y. If these intersection are in tau y, the first component, they must each first component must be in tau. So that means u1 up to un, they are in tau. And if you take their intersection, it has also be in tau, because tau is a topology. In topology, the finite intersection of the elements of tau, it has to be in tau. So this u intersection I from 1 to n ui is in tau. So this implies that, so now here if you look at the right side, so this is the intersection of the y with the element of tau. So by the definition of tau y, we can say that this is in tau y. If this guy is in tau y, then obviously the right side, the one in left side is also in tau y. So that means tau y satisfy all three conditions for the definition of topology. So finally we can say that thus we can say that tau y is a topology on y. And this topology tau y is called the subspace topology. Okay, now let me give you example uh, how to construct the subspace topology on the given subset of a topological space using the topology on that topological space. For that one, let's say X is a topological space whose elements are A, B, C, D, and E. So X is a topological space with those 5 elements. If it is topological space, then there is a topology on X, and let's say X is a topological space with a topology. Uh, Let me call that topology is tau, and whose elements are obviously empty set, the whole set X, this singleton set, and the CD, and also A, C, D, and then now I have B, C, D, E. Okay, so this is our topology on X. Let's consider a subset Y of X whose elements are A, D, and E. So this is obviously a subset of X. Now here we want to construct, or we want to find the topology on this subset Y using the topology tau of X, and which in our definition, which we have denoted by tau Y. So to find the element of tau Y, like I said earlier, what you need to do is you're going to take the intersection of Y with each element or each open set in X. Open set in X, they are basically the elements of the topology tau. So in order to find the elements in tau, what you need to do is we need to take the intersection of Y with each elements in this topology tau. So our first element in the topology is tau is phi, so we need to take the intersection of phi with Y, or intersection of empty set with Y, and then intersection of X with Y, and the third element in the topology is this singleton set. You take the intersection of this guy with Y, intersection of CD with Y. In fact, you take the intersection of each element in tau with Y, and the last one is gonna be B, C, D, E intersection Y. Okay, now we can compute this intersection. So if you take the intersection of empty set with any set, that's gonna be empty set. Since Y is the subset of X, so X intersection Y, that's gonna be Y, and intersection of this singleton set with Y, so that's gonna be our, so it's simply A, because Y has A, and then intersection of CD with Y, so it's gonna be simply D. That's basically the common element of these two. The common element of this guy with Y is D, and then here it's gonna be A and D, because A and D, they are in both this set and also in Y, and then finally the last one is gonna be D, E. Okay, so this is the this one is the topology on Y, and which is called the subspace topology. So this is the subspace topology, and Y with this subspace topology is called the subspace of X. So if we take Y with this topology, then Y is called the topological. Then Y is called the subspace. Okay, all right. So this is an example of the subspace topology on this given on the given subset Y of that given topological space X. Now the next lemma. So I'm going to give you a lemma here without proof. So if you are interested, you can take a look proof from the Munker's book. So this lemma, it tells you how to construct the basis of subspace topology. Okay, here's the statement of this lemma. Let's say X is a topological space. Let X is a topological space and Y is a subset of X. Then the statement of this lemma is, if script B is a basis for a topology on X. Here script B is a basis for the topology on X. Since we are saying X is a topological space, that means there is a topology and the basis for that topology is script B. So if script B is a basis for a topology on X, then this collection script B Y, which is the collection of these sets B intersection Y, such that B is an element of this basis B. So here we are taking this collection and the element of this collections are in this form, B intersection Y, where B is the basis element. So basically the element the element of this collection, they are like, you take the intersection of Y with the basis element of our topology, or you take the intersection of Y with the element of script B. So if you take the intersection of Y with each element of script B, then that collection is script BY, and then this collection is a basis for the subspace topology, on Y. Okay, so this is how we can construct the basis for subspace topology on Y using the basis for the topological space X. So basically what you need to do, if you want to compute the basis for subspace topology using the basis of given topological space, all you need to do is you take the intersection of Y with its basis element. Then that collection is gonna be a basis for our subspace topology. Now let me give you example. Let me call this is example number 2. And this example we have here, let me call this one is example number 1. So example number 2, let's say X, which is the set of real number, and let's consider our standard topology on R. Let's X is R with the standard topology, with the standard topology, and we know that the standard topology on R and the order topology on R, they are the same thing. So we are considering our topological space is the set of real number with the standard topology, that means, or the order topology, and let me just remind you, the basis element of the standard topology or the basis element of the order topology, they are simply the collection of open set, okay, such that A is less than B and A and B are the real numbers. So this collection forms the basis for the standard or order topology on R, which we have seen in our previous lecture or in our previous video. Okay, now here we want to construct the basis for subspace topology on Y, and Y we are taking this interval. So our Y is the closed interval of 0 and 1. Obviously this interval is the subset of R. Now we want to construct the basis for the subspace topology on this interval using the basis of standard topology. So basically what we have here is, we have this real line here, number line here, and let's say this is center 0, and we have 1 here, and this is negative side. So we want to find the basis for the basis for subspace topology on this interval. Now, by using this lemma, uh, the basis the basis the basis for the subspace the basis for the subspace topology on y is simply, let me use the same notation. The basis for the subspace topology on y is gonna be simply what you do is you take the intersection of y is our 0 1, that's closed interval. I'm using this lemma here. You just take the intersection of y is 0 1 here with the basis element of our standard topology, and the basis element in our standard topology, they are always going to be in this they are going to be the open interval, okay, such that a and b are real number with a is less than b. So this collection is gonna be is going to be basis for the subspace topology on y. And if you want to find the basis element explicitly, those basis elements, they are going to be like this, okay. Those this intersection, it depends on a and b. So here those a and b, they are simply real number. They could both real number, they could be inside on this interval 0 to 1, like this one. If both a and b are on this interval, closed interval of 0 and 1, then this intersection is simply going to be the open interval of AB. So the element of this basis, they could be like this open interval of AB if, like here, both a and b are on that closed interval AB. If a and b both are in y is this closed interval. So that could be the basis element here, or that could be an element in this collection, okay. And also since a and b are the real number with a is less than b, those a and b, they may not be entirely inside the inside y or inside this interval. Let's say if b is inside the interval but a is not, a is, let's say a is outside of or on the left side of 0, or let's say a is a negative number, okay. So if this is the, if our a is outside of y and only b is inside, then now the intersection part is simply going to be this one, okay, this half open interval, which is 0 to b if b only in y, okay. And also the same, we can have the similar condition for a could be in this interval and b is outside of y, or b is outside of 0 1. So for example, let's say now let me take, so what you do here is we can take a inside and now b outside. If a is inside and b is outside, now the intersection of 0 1 with ab is gonna be this part. So in that case, our basis element is gonna be like this, okay. It's gonna be a b half, sorry, not b, this one is 1. It's half open interval with 1 is included but a is not. So if a only in y, b is outside of y but a only in y, okay. The other scenario, could be like both A and B, they could be outside of this interval. So for example, like this one, let me erase this one. Okay, so still we are on real line. This is our set 0 1, that's our y. And now let's say our A and B, they could be totally outside of this interval. Like here, this is our A and this one is B. If that is the case, then their intersection is gonna be empty, or something like this. Let's say A is here and then B is to the right side of 1. If that is the case, then intersection is gonna be this interval of 0 to 1, which is y. So the basis element here, it could be either empty set or the whole set y if neither A nor B is in Y. Okay, so this collection, it could have the elements in this form, all the open interval of this form, or the half open interval of that form, or the half open interval of this form, left side open, right side closed, or the empty set or whole set y, or the whole interval of 0 to 1. So these the collection of these intervals and their union is gonna be the basis for a subspace topology on this set y. Okay, so this is how you can find the basis for the subspace topology. Okay, now here let me recall the definition of open set in a topological space. Let's say X is a topological space. X is a topological space with the topology tau. Then U is a subset of X. Let's say U is the subset of X. Is open in X if X is not X, if U is an element of the topology tau. So we have seen this definition of open set in our previous classes, or in our previous lecture, in our previous video. Now here we are interested in open set in subspace. Okay, so this U is the open set in the topological space. Now here we are interested in the open set in subspace. Okay, now let's say Y is a subspace of X with the topology tau y. Okay, since y is a subspace of X, if it is subspace, there is always subspace topology, and we are saying that subspace topology is tau y. Y is the subspace of X with the topology tau y. Then a set U is open in Y if U is an element of that subspace topology. So if U a subset U of Y is called open in Y, it's called the open in Y if that guy U is an element in the subspace topology. So this is the definition of open set in subspace topology. It's similar to the open set in the topological space. If X is a topological space with the topology tau, then U is an open set in X if U is an element of the topology tau. Similarly, if Y is a subspace with the topology tau y, then the set U is open in Y if U is an element of the subspace topology tau y. Okay, now let me just give you an example. So if we go back to our first example, let me go back to our first example here. You can see this is the for this topological space X with this topology, and for this subspace Y, our subspace topology is this one. Now you can see here this guy, uh, this is this, obviously this one is the subset of this set Y. So this is in topology, so this singleton say subset of Y is open in Y. And also this guy, this another singleton set D, which is also open in Y because it's in topology tau Y. But this guy, if you look at the topology tau, this A is in here, so this guy A is open in Y and also open in X because this singleton is in both topology. But the other one, this singleton D, is in subspace topology, so is open in Y. But this guy is not in the topology tau. So this guy, this singleton set is not open in X. So that means you can have a set which is open in subspace but not open in the not open in the topological space. And this is an example. This singleton set D is open in Y because it's in this subspace topology, but is not open in X because it's not in the topology tau. Okay, so here is an example. So in example number one, the example that we had before, this singleton D is open in Y but not open in X. So that means you can have a set which is open in subspace but not open in the given topological space. So here is one more example for that one. Okay, let me give you one more example. Let's call this is example number 3A and the B. Let's consider X is our set of real number, or let's say the topological space is the set of real number with order topology, or you can say the standard topology. Okay, because the standard topology and the order topology, they are the same thing. Let's say X is R. Our topological space is the set of real number with the standard or the order topology tau. And now let's consider this closed interval of 3 to 8. That means we have like this. This is real line and we have center 0 here, and we are taking this closed interval 3 to 8 is a subset of R. Alright, now here we're going to construct a open set in Y, but that is not going to be open in X. So I'm just giving you one more example for a set which is open in subspace but not open in the given topological space. Okay, this we are taking Y which is subset of R, and our Y is this closed interval. Let's take this is a subspace with the subspace topology. Okay, subspace topology. Now, so here let me take the intersection of Y. Let me take the intersection of Y with this open interval. The reason I'm taking this intersection here, so I'm taking the intersection of Y, or intersection of this interval with this open interval 2 to 5. So this is 2 and this one is 5. So this is 2, this one is 5, and if we take the intersection of this one, that's gonna be this half open interval. Okay, which is this half open interval of 3 to 5. 5 is open, 3 is closed. So this obviously this half open interval is an element of the subspace topology, because in the subspace to find the element in subspace topology, all you need to do is you take the intersection of your set Y with the element in the order topology or in the standard topology, and and this open set, since the basis of standard topology or order topology, basis element, they are like the simply open interval. So this open interval, if you take this open interval, that means is a basis element, is also the element in the standard topology. So if you take the intersection of this element of the standard topology or order topology with Y, then this intersection is obviously is gonna be the subspace topology. This is by the definition of subspace topology. So that means this half open interval of 3 to 5 is open is open is open in Y, because this is an element in the subspace topology, but it is not open in R with this topology tau, because this is the half open interval. Okay, and we know that in the standard topology or in the order topology, the open sets are simply the open intervals or their union. Okay, but this is not the open interval, and also not the union of open interval, is the half open interval. So that this half open interval is open in Y but is not open in R. So from these two examples, what we have seen is you can have a set which is open in subspace but not open in the topological space. All right, now the question is, so when we can have a set which is open in the subspace and also open in the topological space, that means when we can say a set is open in both subspace and also in the given topological space. For that, I'm going to give you a theorem without the proof, and that theorem tells us when a set is going to be open in subspace and also in the topological space. So I'm going to give you a theorem without proof. So if you are interested in proof, you can take a look from Munker's book. So this theorem, it tells us or instead of theorem, let me call it lemma. Okay, just that, not the theorem, is lemma. Okay, so let Y be a subspace, let Y be a subspace of a topological space X. Let me call it topological space X. Let Y be a subspace of a topological space X if U is open in Y and Y is open in X, then U is also open in X. Okay, now this theorem, this lemma or this statement, it tells us that if let's say X is a topological space and Y is the subspace of that topological space, if Y itself is a open if Y itself is a open in X, then any open set in Y is also going to be open set in X. So as I said before, I'm not going to give you the proof of this statement, but if you are interested in proof, you can take a look from Munker's book. All right. Okay, so far in this video, we talk about the subspace topology, and in our previous videos or in our previous lecture, we talk about the product topology and also the order topology. Now, the next thing we're going to explore the relation between subspace topology and also the product topology, and subspace topology, and then order topology. So these are the two things that we're going to do in this video. Okay, so we're going to explore the relation between subspace topology and product topology, and also the relation between subspace topology and the order topology. Okay, so the next we are going to explore we're going to explore relations we're going to explore relation between subspace, product, and order topologies. That's what we're going to do next. All right, now I'm going to give you a theorem. That theorem will give us a relation between subspace and product topology. Basically, the subspace topology and product topology on the Cartesian product is gonna be the same, but subspace topology and the order topology may or may not be equal. So this theorem, it gives us the relation between subspace topology and product topology. So as I said before, subspace topology and product topology on the Cartesian product, they are going to be the same thing. Um, um, but the subspace topology and the order topology, they may or may not be. Okay, now I'm gonna give you this theorem without proof. So let me state the theorem. Let's say if A is a subspace, if A is a subspace of X and B is a subspace of Y, then the product topology on A cross B, the product topology on the Cartesian product of A and B is the same as the topology A cross B inherits as a subspace X cross Y. So basically the product topology on A cross B is gonna be same as the subspace topology on A cross B. Subspace topology on A cross B defined by the topology on X cross Y. So this theorem, it tells us the product topology and subspace topology, they are the same topology on the Cartesian product. But like I said earlier, the relation or the relation of order topology and subspace topology, they may or may not be equal. Okay, so just let me write down as a note, then I will give you the example. Okay, the let's say X is a topological space. X is a topological space with simple order relation. Since we are going to talk about the order topology, when you are talking about the order topology, there is always, you need the simple order relation on the on the topological space. That's why we are taking X is a topological space with the simple order relation, and Y is a subspace of X. Then the order topology, then the order topology on Y may or may not be same as the subspace topology on Y. Okay, now I'm going to give you two examples. One of them is you will see those two topology are the same, and the other one those two topology are different. Okay, I need more space. Let me duplicate this one. Okay, I'm gonna erase this one because I need more space here. Let me erase on this slide here. So like I said earlier, I'm gonna give you two examples, and you'll see in one of them those two topology, order topology and the subspace topology are the same topology, and in the other one those two topologies are not same. Okay, so in order to give the example of these two topology are same, we're going to use the example number 2 here. So let's say this is the example for the order topology and subspace topology are the same thing. So what we're going to do is we're going to revisit this example. Okay, so we have already constructed the basis for subspace topology subspace topology on this closed interval of 0 and 1. So we're going to use this example to show the order topology and subspace topology are same thing. Just we are going to revisit that one. That example, let's say X is a set of real number with order topology, and let's call Y is 0, 1, and we have already constructed the basis for the subspace topology. The basis for subspace topology is the basis for subspace topology on Y is, I'm just going to write down, is the collection of the following intervals. Okay, so I'm just going to write down those intervals here from example number 2. I'm not going to explain them here. So the first type, it is like the simply open interval when A and B both are in Y, and the second type, it was like I think it was like this one, 0 B if B only in Y, and the third one, it was like A1 if A only in Y, and the last one, it was either empty set or the Y if neither A nor B in Y. So the collection of those intervals, or the union collection of those intervals and their union is going to be the basis for the subspace topology on Y. Now let's take a look on the basis for the order topology. Okay, now the basis for the basis for order topology on Y. Okay, so if you go back to the order topology, so we have seen that the basis element of the order topology, they are going to be three different type. Okay, one of them is simply the open interval like this one. Okay, and then the other one is the second type. If the set Y has the smallest element, now you can see Y has the smallest element 0, and also it has the largest element or the greatest, or Y has the least element 0, and also it has the greatest element 1. So in the order topology, the basis element is gonna be the collection of the three different type of the intervals and their union, right? So, and one of the type is simply open interval like this one, and the other one is if that set has the least element, then the open basis element is gonna be in this form. Now Y has the least element 0, so one of the type of the basis element for the topology in Y is gonna be something like that one, and also Y has the greatest element 1. So if the set Y has the greatest element, then the third type is gonna be in this form. Since Y has the greatest element 1, so the third type of the basis element is going to be like this. And then if we take their empty union, we can have get empty set, and if we take the union of this interval, then we're going to get Y. So you can see that the basis for the order topology on Y is exactly the same collection of the basis element of the subspace topology. So when you have when you have the same basis for topology, then the topology generated by those two bases are also going to be equal. So here we can say that the basis for the for order topology on Y is the collection of this type of elements, okay, or this collection of this type of intervals here. So the basis for the order topology on Y is the collection of these intervals a b 0b a1 and empty union or Y. Okay, the basis for the order topology on Y is the collection. Since they have those two bases, they have exactly same element, thus the subspace topology and order topology on Y are the same topology. So in this example, we have seen that order topology and subspace topology are the same. So if you go back to the previous slide, you can see in the note we have mentioned that the order topology and the subspace topology, they may or may not be same. So here we just found one example where we saw that those two topology are same. Now I'm gonna give you an example where those two topology are going to be different. Okay, let's say X is the set of real number with order topology, and now let's say our Y, which is the subset of X or subspace of this set of real number. Y is the union of this half open interval with this singleton set 2. So basically we have this, our topological space is the real line, and Y, which is the subspace of R, this one is this interval. Okay, 0 open interval of 0 1, and then you add this singleton. So our Y is this set and then this singleton. All right, now here, so in this example, we're going to show that those order topology and the subspace topology, they are two different. So let's take a look in this. Let's talk about the subspace topology first. In subspace topology, in the subspace topology, now we're going to use this singleton or this outlier. We're going to use this singleton to show that those two topology, order topology and subspace topology, they are not going to be same. So in the subspace topology on Y, this singleton set 2, this set 2 is open because we can write down 2 as the intersection of y with the element in the order topology, and we know the element of order topology, they are simply the open interval, or the basis element for the order topology is simply the open interval. So if we take the intersection of this guy with this interval, let's call is 1.5 to 3. Okay, so if we take the intersection of 1.5, so this one, if we take the intersection, this is 1.5 to, let's call this one is 3. So if we take the intersection of this open interval, which is the basis element for the order topology in R, if we take the intersection of this guy with y, then the common element is simply this singleton set 2. So that's why this singleton set or 1 point subset of y whose element 2 is open in y, because this is the intersection of this basis element for the order topology in y. So this is open in y. That means subspace topology has this element. Okay, now so in order topology, or we can say, but in order topology, this singleton 2 is not open. Okay, I will tell you in a few minutes why it is not open, but this is not open in this set is not open in order topology on Y. Now you can see here in subspace topology, this singleton is open in Y. That means this is an element of subspace topology, but this guy is not open in Y. It's not open in Y in order topology. So that means this singleton is not an element in the order topology. So that's why they are not the same topology. So we just saw one example where the subspace topology and the order topology may not be equal. Now here we are saying that this singleton set is not open in Y in the order topology. This is because let me just remind you the definition of open set in terms of basis. Okay, let's say X is a topological space. Let's say X is a topological space with topology tau, and script A is a basis. It's a basis for the topology tau. We have a topological space with the topology tau, and script B is the basis for topology tau. Then a subset U in X is open if for each X in U, you should be able to find a basis element in script B such that X is gonna be in B and B has to be a subset of U. So this is we have seen this definition in our, I think I guess it was in our very first lecture So we have seen this definition in our first lecture. So this definition, it tells you that a subset U is open in this set X if for each X in U, you should be able to find a basis element such that X is in that basis element, and the basis element has to be open in U. Sorry, a basis element has to be a subset of U. Okay, now let's come back to our example. So here we are saying that this singleton set is not open in Y. If it is open in Y, then by this definition we should be able to find a basis element in order topology such that that basis element is going to be a subset of this singleton set. But that is not possible in because the basis element which contains these two also contains the point of this interval 0 1, because 0 1 is also the part of Y. So let me repeat one more times. So any basis element which contains these two also contains the point of this half open interval. If the basis element contains the 2 and also the point or the also the point of this half open interval, then we cannot say that that basis element is a subset of this guy, because on that basis element, in addition of 2, there is one extra element, right, which is from this interval. But this singleton set has only one element too. So that is the reason why the basis element cannot be the subset of this singleton set. So that's why this singleton set is not open in Y in order topology, but it is open in subspace topology. So that's why the subspace topology and order topology, they are two different, they are not same. So here we found two example. In one of them, subspace topology and order topology are the same, but and in other one, subspace topology and the order topology are different. That means subspace topology and order topology may or may not be equal on the on a set, but the product topology and subspace topology, they are always the same by this they are always equal by this theorem. Okay, all right, that's all for this section.